So today we're going to do a simple problem which I like to call count candy, and it's really similar to the count partitions problem and the count change problem. So our main problem that we're trying to solve right now is actually the count change problem, but in order to explain the count change problem, I think it's better to explain the count candy problem, which is also more commonly known as the knapsack problem. Alright, so what exactly is this problem? Okay, so I'm going to walk through the the count candy or knapsack problem, and the problem is as follows. We're given a bag or a knapsack, alright, and in this case my knapsack can take only 3 grams of weight. Alright. Now in this knapsack, I want to put in candy because that's what I eat for lunch. And for candy, I have a choice between 1 gram lollipops, 2 gram dates, 3 gram granola bars, and 4 grams of French roast coffee. Okay, so I need to use these items and try to calculate the total number of possible combinations of these items that I can put in this bag. So what's one such combination? Right, so for example, we could have 1 lollipop and 1 date. Now, why is this a valid combination? Well, it's a valid combination because we know the sum of the weight of the lollipop and the date is 3. And we want our bag to have exactly 3 grams, and it does, because 1 plus 2 is 3. Alright, so this is one possible combination. So let's examine the process that we used really quickly, in fact, to fill up this bag. We first started out with lollipops, actually. So we started out with our stash of lollipops, and then we moved on to dates, and we actually, in our heads, moved on to the granola bars as well as the French roast. So let me explain. So first, what we did in a very systematic manner is we picked up a lollipop and we decided, alright, do we want to include this lollipop in our bag or not? Like, these are the only 2 possible things that this lollipop can do. It can either go in the bag or stay out. Now let's say we decide to put the lollipop in the bag, right? So if that is the case, then how much of weight do we need to fill up for the bag right now? So we've already filled up 1 gram, and since the bag is 3 grams, we still have a remainder of 2 grams to fill up. Next, after we decided to pick this lollipop, we actually picked up a lollipop again, because we do not know yet whether we want to include more lollipops in a bag or move on to another item. So we picked up another lollipop, and when we picked up another lollipop, we again had 2 choices. This lollipop could either go in the bag or it could remain aside, which is not in the bag. Now let's say we decided we only wanted 1 lollipop in the bag, so we put the lollipop aside. And then we have to pick up the next item that we want to put in. So the next item won't be another lollipop because we decided we don't want any more lollipops. So we pick up the next item, which is a date, because it has 2 grams, which is the next weight after 1, right? Alright, so we picked up the date. An important thing to note right now is the total weight of the bag, or the total amount of weight that we still need to fill in, is equal to 2 grams. So with this date, again, we have the same option of either putting it in the bag or out of the bag, right? So let's consider the case where we decide we don't want it in the bag. So what do? Since we don't want it in the bag, we put it aside, we put all the dates aside, and we pick up the next item, which in this case is a granola bar. But now with this granola bar, do we still have two options? Not really. So the previous two options that we had were either to put the granola bar in the bag or put it aside. But the thing is, right now, the granola bar weighs 3 grams. And we know we need to fill in only 2 grams. So if we do put this granola bar in our bag, we're going to exceed the weight limit. So this is not a possible combination, right? Yeah. Alright, so what would be a possible combination? A possible combination would be the combination we had in the first example, where we had 1 lollipop and 1 date in the bag. And why is that a possible or valid combination? It's a valid combination because the total amount of weight that we still have to fill in the bag is 0 grams. We've already filled all the 3 grams. So that's a valid combination. So we've seen the 2 possible outcomes, right? So one of the outcomes was we filled it exactly, so it's a valid outcome. The other outcome was that we got to a point where if we put the next item in the bag would be too heavy, so it's not a valid outcome. Okay, so equipped with this, you're actually able to solve the count change problem. But quickly, what is the count change problem? Well, the count change problem is that you're given a particular amount of money which you want to find change for. An example would be, let's say we had $8, so this could be partitioned into $1 plus $1 plus $2, right? So this is 4 and $4, right? So this sums to 8. 1 plus 1 plus 2 plus 4 is 8. So this is a valid partition. So let's try and walk through the approach for count change, although I recommend you pause the video and try it out yourself first. Okay, so in the homework problem, it's given that the count change constructor is def count change and amount. So how would you approach this problem? Well, personally, I would just think about doing the easiest part first, and that to me is the base cases. So the base cases are really similar to the base cases we had for the lollipop problem or the candy problem, right? So what are the possible base cases? The 2 outcomes that we had at the end were either that the candy was exactly right for the bag, right? Or the weight of the candy was too much if we included the next candy item in the bag, right? So that would correspond to if if the total amount in the bag that I still have to fill is 0, right? So if amount that I have to fill, this amount, is equal to 0, then I know this is a valid outcome. I'm not sure how to represent a valid outcome yet, so I'm just going to put a comment. Okay, this is a valid outcome. And okay, so let's say, so what is our other case? So our other case is else if our current candy is basically more than the amount we need to fill in the bag, then we know that this is not a valid outcome. So if our current candy value, so current candy or current change is greater than the amount we need to fill in the bag, so greater than amount, then this is not a valid outcome. So of course, in the coin example, in the count change example, this corresponds to if the amount that we still have to partition for the coin is equal to 0, it's a valid outcome, and if the current change is greater than the amount we still have to partition for the money is greater than the money, then it's not a valid outcome, right? So for example, if I was partitioning up 4, and I had already reached, so I had chosen 2 as one of the coins, and for the other coins I decided not to use the 2 coin, and I came to the 4 value coin, then this would not be valid, because 4, the amount I need to fill, or the amount of change I need to get is still 2, right? 4 minus 2 is 2, but 4 is greater than 2, so this is not a valid case. Okay, so I've gotten my 2 base cases almost, but now I notice the next thing I would need to do would be to have a recursive call and make a recursive leap of faith. And for this recursive leap of faith, I can just write it out as, there are 2 cases, right? So if I have my lollipop, I can either decide to put it in the bag or not in the bag. So with the lollipop, or with the particular coin value, so with coin value, if I do use this lollipop, then the amount of weight I still need to fill up after I use this lollipop in the bag would be 3 minus 1, which is 2. So this would be recursive call, and I would use my amount as the current amount minus the current change value, right? Because that's the amount I still need to fill, current change. But I also need to keep track of my next coin, because over here I see I need to know what the current change actually is in the next frame. So because of that, I'm going to have a helper method which will enable me to use this other variable. So this helper method is just going to be called def helper, and it's going to take in amount and current change. Okay. So this with coin value will be a call to this helper method, a recursive call to this helper method, with the parameters amount minus current change and current change, because I would still try to use this coin, the same value coin again, because I haven't eliminated myself from using it, or restricted myself from using it yet. So this is with the coin value, and without the coin value would just be helper, right? And if I don't use this value, then the weight in my bag that I still need to fill remains unchanged. So this will be amount, right? And the current change value will move on to the next value, which is, in this case, in the coin case, it will be current change into 2. Now why is it into 2? Well, it's because our change in the count change problem is given by denominations of 1, 2, 4, 8, etc. So these are coins with values of powers of 2. So this is 2 to the power of 0, this is 2 to the power of 1, 2 to the power of 2, to the power of 3, etc. Right? So that's why it's current change into 2. So for example, 4 into 2 would give me 8. Yeah. Alright, so I've gotten the 2 possible outcomes with the coin value and without the coin value, and I trust them because of the recursive leap of faith. So what I want to return would be the sum of these 2, because with coin value will give me the total number of combinations if I use this one coin, and without would be the total number of combinations if I didn't use this one coin or this one candy. So this would return with coin value plus without coin value, or without. So I named the variable here. Okay, so this will return the sum, and of course I need to make a call to my helper method in this area. So return, and my starting coin will be 1, because that's the coin value I start off with, right? And the amount I need to fill in is passed in by the main constructor, which is amount. So amount and starting coin value will be 1. Okay, and this will actually solve the count change problem that we forgot to mention. What does it mean for an outcome to be valid? What do we do if an outcome is valid? Well, we need to count it, right? We need to count it in as a valid outcome. So if it is valid, instead of writing valid outcome, we're just going to return. Okay, so we return 1 because it's a valid outcome, so we're going to count it as one valid outcome. And if it's not valid, then we would return 0, right? Because we're not going to count that value, so it's 0. And this with coin value, the helper would just basically add together valid amounts or valid combinations and not valid combinations to just sum to the number of valid combinations, right? Great. Again, I walked through it using the candy problem because that seems more intuitive and it's easy to visualize. And it's honestly more fun because who doesn't love candy, right? Great. Thanks for watching. And leave any comments or suggestions or questions in the comment section below. Yeah.